Morning. So our first speaker of the day is Todor Tsankov on model theory of measure preserving groups and actions.
Okay, so thank you very much. Thanks a lot to the organizers for the invitation. I think this is my first proper model theory meeting. I have been enjoying myself very much. So what I'm going to talk about, so all of it is joined with Tomás Ibarlucía, who is over there. And okay, so what I'm going to do, I'm going to make maybe a small survey of what is known about the model theory of ergodic theory, if you want, of measure preserving group actions, and then I'll explain some new results. I mean, the survey part will not be very long because there isn't that much that is known. It's actually quite well, it's a fairly new field. All right, so let me start with the basic setup. So this is the basic setup that you normally do ergodic theory in. Okay, so you fix some countable group, which very often says the group of integers, but for what I'm going to do, I'm just fix some countable group. And then you have a probability space. Okay, so a probability space, it has three components. So it has the space, it has the sigma algebra, and the measure, which is defined on the sigma algebra. And then also the group acts on this space by measure preserving transformations. So it acts by measurable automorphisms, so bijections that are measurable with respect to the sigma algebra and that preserve the measure. And preserve the measure just means this, that when you have a set and then you translate it by some element of the group, it still has the same measure. And here. Okay, so now I'm going to make a convention that I'm going to follow throughout the talk. So if I have two elements in the algebra, sets of measurable sets that differ on a set of measure 0, I'm just going to identify them. Okay, so I just divide by this equivalence relation, which is on sets to differ on sets of measure 0. And then if I do this curly x, the algebra, it actually becomes a metric space. Okay? Then I can measure the distance between two sets just by measuring the measure of their symmetric difference. Okay, so this is what is written here. This is the distance. And so with this, it becomes a complete metric space. And there's also, of course, it's an algebra of sets, so it has a bit more structure. It's a Boolean algebra, right? You have intersections, complements, unions, and things like that. Okay, and then the group gamma. The action on X, of course, it is coded by the action on measurable sets. So the action on measurable sets, just then you have to say that this action is by isometry. So isometry just means it preserves the measure, and of course, it has to preserve the Boolean algebra structure. This is clear. All right. So before I go on, I'll just give you a couple of examples of measure preserving group actions, sort of the things that we are interested in. Okay, so one of the most important examples in ergodic theory is the Bernoulli Shift. So your space is 2 to the gamma, so gamma is your group, and then your space is just sequences of zeros and ones, which are indexed by elements of the group. So whenever if I don't specify the measure algebra, you just take the algebra of all Borel sets. Yeah, there is basically only one choice. Okay, but then I have to tell you what the measure is. Okay, so I choose some number p between 0 and 1, and then I put say weight p on 0, weight 1 minus p on 1, and then I independently choose for every coordinate. I independently toss a coin and choose what value to put, 0 or 1. Okay, so this gives me a measure onto the gamma, and then the action is just by shifting. Yeah, if I have my sequence x, which is indexed by gamma, I will take the sequence and I shift it by some element of the group. And this is known as the Bernoulli Shift, of course. So this action preserves the measure, and it's a nice measure preserving action. And in fact, it's practically the only thing you can do for a general group. This is the only action that you can write down for just a general countable group gamma. Of course, if you have specific groups, you can do a lot more things. But for a general group, this is practically the only thing. There are other actions. The question is that you cannot write them down. Okay. So there is a second example which will be important for what comes later. Those are so-called compact actions. So here you need a little bit more data to start with. So you need a homomorphism from gamma into a compact group K. Okay, so just take any homomorphism like that. And then you have some closed subgroup L of K. Okay. And then you can make gamma act on the homogeneous space K by L just by using the homomorphism. Right? So what to do, to act on a constant gamma L, and you have gamma, so you take the image of the homomorphism and then you just translate on the It's a simple thing, so you translate. Now, okay, you have to put a measure. So the measure is just take the Haar measure on the K, and then you take the quotient measure on K by L. And so this is a measure which is preserved by this action, yeah, because the Haar measure is translation by N. And actually, in many cases that I encounter, the group L will be trivial. And this is a perfectly valid thing, so you can just take L to be trivial, and then gamma acts on K by translation. Okay. So this is all right. So here I put. There are a couple of examples, sort of very classical examples of actions like this. So the first one is the irrational rotation. So you just have a circle, then you pick some irrational number alpha, and then you just rotate the circle by alpha. Okay? So this is an action of this type. Okay? And also another very similar action is called the odometer. Now instead of the circle, your group is the dyadic integers, and then what you do is you just add 1. Right? So Z embeds into the dyadic integers, and so you just act by translation. Yeah? So your measure preserving transformation, if you want, is just you add 1. So this is also a nice and important example of a measure preserving group action. Right. So first one.
It's usually called two-adic, and dyadic means rationals.
Ah, really? Okay, I'm sorry. This is because, I don't do algebra, so my terminology is
clearer.
Okay, thanks. Alright, so there is also this notion of substructures, which will be, if you want, I'm going to consider this in a model-theoretic setting in a second. So I'll tell you what substructures are, even though I didn't tell you what structures are. I suppose it's not so hard to guess. Okay, so what is a subsystem, if you want? Okay, maybe not call it a substructure, let's call it a subsystem. So you have a system which is gamma acts on X, but remember, what I care about is the algebra. Okay, so just a substructure, will just be a subalgebra of my measurable algebra, which is closed, so it is closed in this metric, and is also invariant under the group. Right? Because but the group also has to act on it, so I better take an algebra take a subalgebra which is invariant. Okay, so this is one way to view it. This is one way to view this substructure.
You really mean sub sigma algebra?
Yes, but once I say it's closed, sigma is automatic. So the thing is, countable additivity just comes from continuity. So if I just have a subalgebra which is closed in this topology that I defined, it will automatically be countable.
Okay, fine.
So again, you say, so you look at this as a Boolean algebra.
Yes.
But what about the Borel structure?
What do you mean the Borel structure?
Is it also a sub? Is it closed under countable?
Well, this follows from continuity because it is a closed set. Yeah, it follows from the fact that it is closed.
Why are you so why are you interested in the Boolean algebra structure specifically? Why is this
I'm going to say this in a second. Okay. So the thing is that there is a dual picture, which is what people often do. To define a subsystem. So what you do, you take. To every algebra like this, every closed subalgebra of the measure algebra, it actually corresponds to a factor map. So instead of looking at dually, instead of looking at a subalgebra, I can look at a map from X to another space Y. Right? This X is different from the other X. Right? So this is just the space X, so I can look as a map from X to Y. Then I can push the measure forward, and then I have a map like that. And now to get the algebra, what I do is I pull back. All the measurable sets in Y, I pull them back in X. So this is a way to obtain a subalgebra. But also conversely, every time I have a closed subalgebra, I can produce a Y like that. Okay? So it's important to understand this. So those are those two dual views of substructure. So both of them are important, and then I'll use both.
Do your spaces have a topology?
The space does not have a topology,
no.
But the algebra does.
Well, you deduce a metric on the algebra.
That's right. So the space does not have a topology.
Space is just a metric.
Space is just a set,
yes.
And then with cubed with sigma.
There's no Borel.
There's
no Borel.
There's no Borel, yes.
Oh, there's no Borel.
But this is just a general fact that every time you have a subalgebra, you can actually get it from a factor. Close, yes. You can get it from a factor. Okay. And then of course I want gamma to act on Y, right? And so this means that this thing is gamma invariant. Okay, so this is, it's usually, so in ergodic theory this is called a factor, right? It's not called a subsystem, but it's usually called a factor. This comes from this viewpoint, that it actually can be represented as a factor map from X to Y on which Y acts. I'm going to give examples of this, well, not right away, but soon. Okay, so now I'm going to, so after I introduced yesterday continuous logic and explained everything about it, I'm just going to... Well, at least this is what I thought he would do when I was preparing my slide. Anyway, so I still prepared a slide that reminds you the main features of continuous logic. So, of course, I'm going to look at the whole thing in the setting of continuous logic. I hope this was also it's clear. So just, I've made a few bullet points that remind you the differences between continuous and classical logic. Alright, so first of all, structures are not discrete sets, but they're complete metric spaces. Yeah, so in my case, of course, the structure will be the measure algebra. Okay, maybe I should emphasize this once again. So the structure is not the actual set X, it's not the space, but it's the algebra of sets equipped with this distance, which I just defined. Okay, so this will be my structure. Okay, but in general, structures are complete metric spaces. So equality is replaced by a distance, so by a metric. So you can only talk about things approximately, basically. You cannot say the two things are equal, but then you can say that you're close to each other, things like that. Then so instead of relations, you have real-valued bounded uniformly continuous functions on your space, on your structure. And functions are the same thing. I mean, functions are just function symbols are just maps from your structure to itself that are uniformly continuous. So connectives, okay, so this is an important difference. So in classical logic, connectives are Boolean functions, right? You have a Boolean function from 2 to the k to 2, and then if you have set like 10 formulas, you apply some Boolean function, and then you get another formula. Okay. You often don't do it like this. Yeah? You often use a complete set of connectives, say conjunction and negation, and then using those you can express all other Boolean functions. This is one of the few useful theorems in propositional logic, that there are complete set of connectives which are actually quite small and explicit. So here you do the same thing, instead of, because now formulas are real valued, or you have to combine them using continuous connectives, right? So you have an arbitrary continuous function from R to the k to R, then you have some formulas, and then you can combine them using this function, and then you get a new formula. Okay, and in the same way that there is a simple complete set of connectives in the Boolean setting, so here you can also take, for example, if you don't want to write any continuous function, what you can do is you can start with, say, addition, multiplication, and the constants, and this is enough. Yeah, this is a complete set of connectives. So you can just addition of formulas, multiplication, and you have constants, and that's all. Alright, and quantifiers, so instead of the classical quantifiers, because, again, formulas take real values, you have sub and int. Okay, this is not much to say about that. It's also closed, okay, this is sort of a technical condition that I'm not even sure I'm going to use, but so uniform limits of formulas are, again, formulas. So if you have a sequence of formulas that sort of converge uniformly, you can take the limit, and this is still somehow in your, it's still a formula if you want. Okay, and then finally, okay, this is just to emphasize what I said several times already, that if you have any formula, and if you have a model, of course you can interpret the formula in the model, and it is interpreted as a function, right? So it's a function from m to the n, from a power of the model to the reals, which is bounded and uniformly continuous. And well, one of the points is that this bound and the modulus of continuity can be determined syntactically from the formula. Okay, so there are syntactical properties of the formula. I mean, say the interval that it takes its values and the modulus of continuity. Okay. So this was a crash course in continuous logic. I mean, I secretly hope that most of you have seen this stuff before. Alright, so now how do we code? So how do we code this situation? I mean, the ergodic theory situation in the setting of continuous logic. Okay, so what do we do? Right, so the structure, as I said again, is the algebra. Okay, it's the algebra of sets. So the language is with the language of Boolean algebra. So you have intersections, complements, and unions. And then we have a single relation, which is just the measure. Right, so we have the measure, which is a relation, takes values, well, relation is a predicate, whatever, it takes values in the interval 0, 1, and you can apply it to any set.
But it's a function.
Well, it's called in continuous logic, it's called a predicate. It's not a function, okay. You see, a function symbol, I mean...
Sorry, I'm being facetious, sorry.
Alright, so it takes, I mean, the measure is this predicate, it takes values in 0, 1. And then with it, of course, you can define the metric, right? Because once you have the Boolean algebra structure and the measure, the metric is definable from that. Okay, and then here I put a few axioms. Actually, I noticed, I mean, as I said, this is my first model theory meeting, and I noticed that it seems to be in poor taste in a model theory meeting to write actual formulas. But I somehow didn't know this, so I wrote some... I actually wrote some formulas that axiomatize the measure algebra. Okay, so I mean, I didn't write all of them. So for example, you can write something, I mean, just universal axioms like this. You can write that it is a Boolean algebra. Maybe here what I wrote is that the thing is distributive. So the intersection distributes with unions. And then, okay, you can write a few more like this to axiomatize the fact that it's a Boolean algebra. Then you have to say it's a measure algebra. So you have to say that, well, this is the additivity of the measure, basically, right? That the measure of the union is the measure of the other two minus the measure of the intersection, something like that. And then, okay, there is a last condition, so I haven't talked about this yet. So I want to assume most of the time that my measure algebra is non-atomic. So non-atomic just means that there are no atoms. Yeah, there are no points in X that have a positive measure. So this you cannot express right away because you cannot talk about points. Right? The only objects in your logic are the sets. So the way to express it, you express it indirectly. You just say that every set can be split into two. So let me okay, let me read this for you because here there's an important feature of continuous logic that appears. So let me just read the formula. So it tells you that for every A and for every epsilon, there exists a B such that when you intersect B with A, it cuts approximately half of A, so the approximate is up to epsilon. Okay? So what I should say, what this formula does not say, is that there is a B that actually cuts exactly half of A. Okay? And this is extremely important in continuous logic. I mean, this is really one of the main points. That those are things that you cannot say. So you cannot say that there is something that does something exactly, but you can say that it does it up to epsilon for every epsilon. Yeah? So this is what happens here. This, of course, is enough to say that the thing is non-atomic. Alright, so just, I mean, if you just put those axioms, I mean, there's no group for the moment, so you get so a complete omega categorical, omega stable theory. Okay, so this is basically what codes probability theory, if you want, in model theory. And this, of course, this is a theory which is very well understood.
This was done by Itai before.
Oh,
Itai.
Of course, yeah, this was done a long time ago by Itai, I suppose.
Yeah, I know. I remember.
Yeah, sorry, I mean, I think most things in continuous logic are done by Itai. I mean, Alright, okay, so now how do we code the, okay, the group action? Right, so you have, okay, so you have this space, I mean, this we already have, and then for the group, what you do is you just put a function symbol for every element of the group. Okay? And then of course you have to add a few more axioms, so you have to say that every element, every gamma, is an automorphism of your structure. So automorphism that also preserves the distance, which implies measure preserving. Okay, and you also have to code the structure of the group. I mean, you have to say what group is active. Okay, so this the way you do it, you just take, I mean, for every, if you have n elements, gamma 1 up to gamma n, and if they happen to, if their product happens to be the identity in gamma, right? If this is a relation in the group, well, what you do is you say that it has to act as the identity on your space. Okay, so that's all. So, well, a basic remark is that if your group happens to be finitely generated, you don't have to put an element for every element of the group. It's enough to just put things for the generators. And then you put those things here for the relations. That's enough. Okay. For example, if the group is just the integers, you can just put a single function symbol for the generator. Alright. Okay, so there is another concept that comes. So an action, I mean, we don't want to look at arbitrary actions because, for example, a group gamma could act through its quotients. Right? If, say, gamma is a free group or something like that, it can just act through a quotient, and then it's not so interesting. So this is a strong, if you want a strong non-triviality assumption on the action, is freeness. So free just means that non-identity elements have no fixed points. Okay? Which basically means that every orbit looks like the group. Right? I mean, just every orbit is just a copy of the group. So you have, I mean, the orbits are just copies.
Do you want a generating set just as a semi-group or as a group? I mean, it seems a bit inconvenient in general.
So maybe you want it as a group. I mean, maybe you want a sort of symmetric generating set so that you also have the inverse.
You don't have a symbol for gamma inverse, just for gamma, yeah?
Yes.
Okay, so you need quantifiers in order to.
Yeah,
a general
I suppose it doesn't matter too much, but it's probably more convenient to also put the inverses in the beginning. Let's not care about it. So I'm not allowed to quantify over elements of gamma. Yeah, this is. I'm not allowed to quantify over elements of gamma. Those are functions.
No, of course, but it might not be the same all the time. Okay.
Okay. Yeah. So if you want to do sort of things like that, it's probably important what language you choose. I agree. Alright. So this is the definition of a free action. So as you see, this is not. It's not completely obvious how. I mean, this again talks about points, right? It tells you that the elements have no fixed points. So again, if you want to write an axiom, okay, so you have to do something. So let me say what the axiom is. So again, you say that for every A, again, I just drop the last formula I write. Okay, but so you say that for every A, there exists a B. Okay, for every epsilon, so there exists a B, such that first B is almost contained in A. Okay, this is the first thing. And then it says that B, you can move it away from itself by gamma. And the measure of B has to be well, more or less approximately 1/3 of the measure array. I mean, this I don't care so much, but it has to be, it cannot be less than epsilon. I mean, I have this error, epsilon error. So if I don't put the last part, then it's a problem because the empty set will satisfy this, and then this is not good. So I have to say I have to put a strong condition that B is non-empty. So I just have to say that it's more or less close to the measure array. I mean, you get used to this sort of thing. I mean, once you start actually writing formulas in continuous logic, I mean, used to that. Okay, and so now we get a theory, right? So we put all of those axioms together. And so we call this theory, the resulting theory is FR, so free actions of gamma. So what it calls is free measure-preserving actions of gamma on a non-atomic probability space. So you put all of those axioms that I told you, and then you get a theory. Okay. All right. So there is, so the first thing is, so it's for amenable gamma. Okay, so now if the group gamma happens to be an amenable group, maybe just a quick reminder, I think this already appeared in one of the talks. So a group is called amenable if there exists a left invariant probability, so left invariant finitely additive probability measure of the group. So typical examples of groups like this are, of course, there are finite groups, abelian groups, so more generally solvable groups, but there are also other things to make out of those and complicated things. And the typical non-example is the free group. And also because amenability is closed under taking subgroups, this means that anything that contains a free group is not amenable. So this is enough. I mean, if you don't know what amenability is, I think no. There's a huge theory about this in group theory, of course. About amenability. Okay, but there is a very important dichotomy in ergodic theory between the amenable and the non-amenable. I mean, it's probably not completely obvious why having a left invariant probability measure on the group actually makes any difference about its actions, but it's a huge dividing line. So I'm not going to get into this. But okay, so there's this theorem, so which is basically essentially due to Ben Yaacov, Berenstein, Henson, and Usvyatsov. It is in this paper, the long paper on continuous logic, which is practically the only reference. Okay, that says that if gamma is an amenable group, then this theory, which I just told you, is a complete stable theory that eliminates quantifiers. Okay, and this theory is omega categorical if and only if the group is finite, which is basically the non-interesting case. Okay, so if the group is finite, you don't do dynamics. So you generally don't care about finite groups, you only do infinite groups. And then the theory is not omega categorical. So I should say, so they actually prove this theorem only for the gamma equal to z. But there's machinery, so due to Ornstein and Weiss, which allows you to basically generalize the proof to an arbitrary group. So this is the case, and this is a very nice theory. In the case if the group is amenable, so you have all of those properties, and then you can do model theory.
And without amenability, do we have any properties of this theory, or it's completely difficult to say?
So none of those things. Well, okay, it's not clear. So in general, it's not clear. I mean, there are certainly groups for which all of those are false. For arbitrary groups, it's not clear. So I mean, I'll get to this. I mean, I mostly talk about non-amenable groups. Okay, so maybe I just want to say one thing before I go on. So it's a very nice model-theoretic setting. So I certainly encourage model theorists to look into this. But the thing is that, this theory, so the ergodic theory of amenable groups, it's a very old and mature theory. So people sort of can answer most questions. Actually, so the most, if you want the last important open question in ergodic theory of the integers, just of a single transformation, it was answered like a couple of months ago by Tim Austin. So there isn't really that much left to do in ergodic theory proper. So, if you want to do model theory, of course, there's a lot of things to do in model theory, because almost nothing is done. But if you want to apply it to ergodic theory, which is sort of my motivation, I actually want to get results in ergodic theory, then this is not really probably the best setting, because it's difficult to get new results, because the theory is already so well understood. Okay. Alright, so this is the case for amenable groups, so I'm not going to talk about amenable groups anymore. Alright, so we need some more definitions. Let's go on. So, ergodicity. So this is it's one of the most fundamental notions in ergodic theory, as you can guess from the name. They actually chose to name the whole theory after this concept. Alright, so transformation is called ergodic if there are no non-trivial invariant sets. So if you want, it means it is indecomposable, right? You cannot split your system into pieces, so both of them is, if you want, the system itself. Alright, so here is, I wrote it here, so it means that for every set in the algebra, if it is invariant under the group, then it has to be trivial. It has to have either measure 0 or... Okay, so this is the definition of ergodicity. And then there is this thing called the ergodic decomposition theorem, which tells you that every system decomposes as an integral of ergodic components. Which basically means that if you want to understand a measure-preserving system, it's enough to understand ergodic systems, because then everything decomposes in a canonical way as an integral of ergodic system. So you can just restrict looking at ergodic systems. All right. Okay, so examples, I mean, so of those things, the examples that I gave you before, so the Bernoulli shift is always ergodic if the group is infinite. And if you have a compact action, well, now there is a condition, I mean, for this to be ergodic. So the morphism that you started with, so the morphism of gamma into k, needs to have a dense image. Okay, so basically it's if and only. So the system that you get is, so it's ergodic if and only if the morphism has a dense. Okay. But unfortunately, even though it's a very fundamental concept, it actually is not an elementary concept. Yeah, it's not first order. So you cannot express this in first order. So okay, so this follows. I mean, for example, it follows from the previous theorem, because the theory that I told you, I mean, there was no axiom about ergodicity, and the theory is still complete. And of course, for every group, you have free actions which are ergodic and other actions which are not.
Don't they have bounded cardinality?
What is bounded cardinality?
Ergodic actions.
Yes. I mean sure. So okay, this is another. If you know, this is another.
Can't be action, but
yeah.
What? No.
No, they don't.
Well, you have strongly ergodic and these are.
I think those should be a bounded cardinality. I mean, no, maybe not. Okay, maybe not.
Properties.
There's a property T. Okay, so I think I take this back. So there are groups for which ergodicity is actually is an elementary property. No, okay. Of course, I mean, if you take, so I take this back. So if you take, instead of 2, you take any measure space. I mean, instead of 2 to the gamma, you just look at any measure space at all. And then you look at this product, it is still an ergodic action. And of course, then the base can be of arbitrary continuity.
Yeah.
Okay, so, sorry, I take this back. All right. But anyway, so it is not an elementary property because of the previous theorem. You can also look at this, I mean, what I wrote. Okay, so it sort of resembles first order formula, except that first of all I have this quantifier over gamma, which is not great. But this is actually not the point. I mean, the thing is that even if the group is finitely generated, in which case I only have to say finitely many conditions of this type, but this is not the point. The point is that this condition on the left, that gamma A is equal to A, this is what is not first order. I mean, this is something which is not actually, there's no formula that tells you that gamma A is equal to A. I mean, you can only say that it is close to A, and then it's not the same thing. Okay.
Don't you get equality in a saturated model? This equals equality in a saturated model.
That's correct, yes.
Yeah. And
But it's in the if part.
but I mean, what?
It's in the conditional part.
Yes.
Otherwise.
So there's infinitely many formulas, right?
Yes, it is what is called a type definable thing. So if you look at all invariant sets A, so if you look at all subsets A of your algebra which are invariant, this is not a definable set. It is what is called, I think, a type definable set.
Oh, okay.
So that's why you cannot make a formula like this. Okay? All right. So, but as well, people mentioned, so there is actually a notion which is first order, and this is what is called strong ergodicity. Okay. So let me define this. So you have a sequence of elements of your algebra. You say that this is asymptotically invariant if the following 2 conditions are satisfied. Okay. So first, the measures. So the sequence is non-trivial, so it does not converge to the empty set or to the whole thing. So I mean, the measures say converge to some number which is between 0 and 1 strictly. And second, for every gamma, the sequence becomes more and more invariant. So once you fix the element of the group, the sequence just becomes more and more invariant. Okay, so this is what is here. And so an action is called strongly ergodic, well, if it has no sequence like that. Okay, so this is a strengthening ergodicity. And now, of course, this, so one way to say this is that if you want the saturated model or the ultra power is ergodic. So a system is strongly ergodic if and only if its ultra power is ergodic. Right, because if you have an almost invariant sequence like that, I mean, when you take the ultra power, when you take the limit of the sequence, it gives you an invariant set. Yeah. And this, of course, is a first order property, because now it is actually, there's a finite condition that implies that the set is not invariant. Okay.
There's no such sequence. So
okay, by an elementary property, I just mean something which is invariant under elementary equivalence.
Yeah, but it varies from, you can be strongly ergodic in many different
That is correct,
ways.
yes. This is correct. So so it's not, there's no formula that explains that actually writes strong ergodicity. There's not a single formula that does it. But by elementary property, what I mean is that it is, an invariant of elementary equivalence. Okay.
So really, it's the class of models which is the collection of things elementary equivalent to ergodic. Is it that? Is it somehow the closure of the ergodic?
No, it is what? No, it is the other way around. It's exactly the duo of this. It is the class of things which everything in elementary class is ergodic.
No.
Yes.
What?
Strongly ergodic.
Means?
There's negation.
Oh, I'm sorry. This implies ergodic.
Yes.
I'm sorry. Of course. Yeah. Sorry.
Okay.
All right. But it's more strongly.
Okay. So there is a. I mean, strong ergodicity again is an important concept in ergodic theory. So they do not happen for amenable group actions. So amenable group actions do not admit strongly ergodic actions. So actually, this is an equivalent thing. So a group. There's some negation. So amenable groups. So gamma is amenable if and only if the Bernoulli shift is not strongly ergodic. If and only if every action is not strongly ergodic. Okay. So this is, if you want, is one way to detect amenability is via those strongly ergodic actions. Right. Okay, so I hope the definitions are okay. So this is a problem, right? So for non-amenable groups, this is what Christoph asked. So there are no, I mean, we don't know any natural complete theories. Okay, if the group gamma is non-amenable, I mean, before, so for amenable groups there was this very simple theory which was complete and eliminates quantifiers and whatnot. But for non-amenable groups we don't know any. I mean, there isn't a single known theory which is complete. Well, sorry, I mean, there isn't a recursively axiomatizable, non-recursively axiomatizable complete theory, if you want the precise thing.
But they're natural structures.
That's correct, but their theories are not known to be decidable.
So what?
So it is, if you don't know what the axioms are, it's a bit difficult to study the theory. This is all. Sure. Okay. Maybe this is not a problem, and I'm not. This is a philosophical question. Anyway, so we're also. I mean, this is another part of our project. So we're actually trying to find things like this, also things like model companions and so on. But
can you give an example of a definitely undecidable one?
For a?
Can you give an example of a definitely undecidable theory like that?
No.
Oh.
But there exists because I mean there are results that there are continuum many of those. So
that doesn't necessarily. I mean,
yes.
Oh, continuum many in account for
in a fixed language.
Yeah,
That's correct. Yes.
To generate.
Yes. So some of them are not decided. This is not a very satisfying argument. No. So the those theories are not understood at all. So I cannot. I'm sure it's possible. I mean, if you want to get an undecidable one, I'm pretty sure this is possible to do by.
Yeah.
But we haven't tried. All right. So, but then what people did actually is, I mean, okay, you don't understand the full first order thing. Okay, you can restrict yourself to existential forms, and this is what people did in model theory in the 70s.
No, I think I asked a stupid question because you can just get the theory of the group, right? You can just, if you have two generators, then you can just ask about identities in the group, and that's going to be undecidable and continuum. So,
no, but even say for the free group, I mean, even for the free group, I think you can get an undecidable theory.
Yeah.
Okay, so this is not, it does not come from the group, but from the action.
But can you get high quantifier levels?
I don't know.
Okay.
So what I know is about the low quantifier levels, which is about existential formulas. Okay. So what's an existential formula is just a formula of this type, where we say that inf over some tuple phi of x, where phi is quantified. Okay? I'll just call this an existential formula. I mean, if you change conventions, you can put a sup if you want. I mean, so an existential statement, right? This is a formula. So an existential statement is that you have to say that a formula like this is small. And then if you say that an inf is small, this is an existential statement. So this is how you should think about it.
Shouldn't it be something that goes up substructures?
Yes, this is okay. This is the next step. All right. So this is okay. So this is a definition that was made. I mean, this weak containment thing, which is here. So this is a definition that was made by Kekris maybe 10 years ago. It had nothing to do with model theory. I mean, it was inspired from a completely different thing, and the definition was quite different. But it turns out it is equivalent to actually what I wrote here. Okay, so let me read it. So if you have two systems, x and y, you say that the system y is weakly contained in the system x. So this notation. If for every existential sentence, it actually takes smaller value in x than it takes in y.
So okay. Y is a substructure of x?
Y is a substructure. No, y is not a substructure of x.
Oh, I'm sorry.
For example, if y is a substructure of x, this is definitely true. But this is a weakening of this. This is what's called weakly contained. Oh. You see that the words, I mean, when you say weakly or strongly, they're actually meant to help you.
Okay, so, no, yeah.
All right. Okay, and then you say that they're weakly equivalent if they're weakly contained in both ways, which means that for all existential formulas they agree. Yeah, so if you have existential formulas, they take the same values on your two structures. Then you say that they're weakly equivalent. Okay, so there is an equivalent condition which I put here in parentheses, which maybe is a more, I don't know, for model theories maybe it's an easier thing to, I mean, it's a semantical condition. You just say that y is a factor of an ultra power of x. Okay.
But again, this means a substructure.
Yeah, a factor means substructure, yes.
Yes.
So this is what a weakly contained is. Okay. So if you want the existential theory of y is contained in the existential theory of x, if you want. All right. Okay. So here are some basic facts which, yeah, okay, I think I have some time. So I'll go through this. I mean, this is not really very relevant for what I'm going to do after, but just sort of to give you some intuition about the notion. This is actually something that people have looked at quite a bit in the last 10 years in ergodic theory. I mean, it's surprising it may sound, but this notion is actually it's an important notion that people look at. Alright, so first of all, if gamma is amenable, then there is nothing. I mean, there's only one weak equivalence class because, as I told you, the theory is complete. I mean, already the complete first order theory is complete, so of course there's only one existential theory. So an action is okay, is strongly ergodic. I mean, this is one way to express it. It's not an existential statement. Sorry, the negation of strongly ergodic is an existential statement. So you can express it by saying that the trivial action, so something is strongly ergodic if the trivial action is not weakly contained in it. Just one way to write it down. Think a little bit. So there's, okay, now the next one is actually an actual theorem. So it's a theorem of Aber and Weiss, which tells you that this weak containment, it always has a minimal element. So if you look at the Bernoulli shift, it actually is, so it has the smallest possible existential theory, which means that you can simulate, yeah, you can simulate the Bernoulli shift in any free action. So if you have just some sort of existential statement, you can actually simulate this in the Bernoulli shift. Okay. Sorry, the other way around. Take this back. So if you have any situation in the Bernoulli shift, you can simulate it in any action. Okay. This is the way it goes. All right. And the next one, this is a recent result of Louis Bowen and Robin Tucker-Drove, that if gamma contains a free group, then there actually continue many. So weak equivalence classes, if you want existential theories, of free strongly ergodic actions. Okay, so you can put, so you put free, you put strongly ergodic, and you still get continue many different existential theories. Okay, I mean not compatible. So of course this implies that you have continue many first order theories and. Alright, then it's open whether this thing extends its nature. It's a question that was asked also a long time ago, whether you can do this for any non-amenable gamma. Okay, so it's, I mean, this is only, so they only did it for gamma that contain free group. So as I said, I mean, this, if you want, this is indicative of this dichotomy between amenability and non-amenability, which I mentioned. So in the amenable case, you only have one, and here you have continuum many. And there are many things like this. Okay, so this was just the general culture slide. Alright. Okay, so this is, I mean, what we started to do, and we basically started with this theorem of Yuanov and Tucker-Drove. So it's it's called the rigidity theorem. I mean, it's an instance of a rigidity phenomenon. Okay, so let me read the theorem. So it tells you that if X is a compact action, so remember, compact was this is given by this morphism in a compact group, and Y is strongly ergodic, so if you have those two things, and moreover, X is weakly contained in Y, so the existential theory of X is contained in the existential theory of Y, well, then actually X is a factor of Y. So this is the dream world of analysis.
Can you remind us what a compact action is?
Yes, compact action is an action by translation on a compact group with the harmony.
Yeah, homomorphism.
So it's really like a finite thing. This is
no, it's like I mean, it's like irrational rotation, for example. I mean, see, the measure algebra is not a finite thing. I mean, the measure algebra is just this big.
Oh, I see.
I mean, there is some finiteness thing. I mean, this is the whole point. But you have to.
No, you mean it's finite in the sense of.
No, it is not finite. It's definitely not a finite system. No.
What?
It is not a compact. So the structure itself is not compact.
Yeah.
Okay. It just comes from something which is compact in a special way. Alright. So this theorem actually generalizes a previous result by Aber and Elek, who proved the same thing, but when X is finite, rather than compact, it's actually finite.
When it's finite, it's kind of obvious from model theory point of view.
Probably, yes. But then I have to be a little bit careful because no, it's not true. The strong ergodicity assumption is necessary. Okay? So you have to actually find a way to use this strong ergodicity. So if you remove strong ergodicity, this thing is false. And the finite one is also false. For amenable group, this is always false. So there is something. I mean, even in the finite case, there is something to this theory. Okay. All right. So here you get, I mean, there's an easy corollary of this theorem that now if you have two compact actions that are strongly ergodic and weakly equivalent, then they're actually isomorphic. So why does this happen? Well, because from this you get that they are bi-embeddable, right? I mean, one is weakly contained in the other, so they're, I mean, one embeds in the other, then the other embeds back. But compact actions are known to be what is called coalescent. That if you have a self-embedding, it's actually an isomorphism. Okay? And so you just have, you get embeddings in one directions, you compose them, so you get a self-embedding, and then it has to be an isomorphism. So actually, the both embeddings were already isomorphism.
Do they exist?
Compact strongly ergodic actions? Yes. There are many of them.
Yeah.
Yeah, I mean, I'll get to this. For example, okay, I can tell you something now, which is on my last slide. If you have a property T group, every ergodic action is strongly ergodic.
What group, sorry?
Property T.
But can it be compact? I mean,
Yes. You just take a homomorphism from a property T group into a compact group. So they also exist for the free group, but it's harder. I mean, essentially there is some number theory involved. But okay, I mean, I'll get to this later. Yeah. So questions? Okay. So this is the theorem that we sort of.
If an action goes through a homomorphism into another group and it's strongly ergodic, doesn't it mean that already the action of the other group is strongly ergodic?
No, it depends. No. I mean, if you mean about the compact action, no, I mean about the compact group acting itself.
The compact will not act strongly ergodically itself?
I haven't defined this. I mean, it have to be, what does this mean? I mean, I only define this for, I mean...
I thought it meant that there are finitely many elements, such that any measure have set.
Oh no, then this is definitely, if you say finitely many is definitely false.
Okay, so I didn't understand. Okay.
No, for countable groups, yes, but not for...
I thought strongly ergodic was equivalent to saying that there's a finite set of elements in the group, such that for any measure half set, one of them moves it.
That's correct, yes.
By a noticeable amount.
That is right.
Okay. So I think later.
Okay, then I'll talk about this later. Okay. But there definitely do exist compact strongly ergodic actions. What just happened? Sorry about that. What happened? So why did it oh, sorry about that.
We have a chance to see the definitions.
Alright. Okay, so this is for compact action. Okay, so this is now the last definition. Okay, so we have to pay attention a little bit. This is probably the most technical definition that I'm going to give. But this is what the main theorem is about. Okay, so alright. Okay, so you start with the measure preserving system, so things that we looked at until now. So we have X mu, so it's a measure preserving system of gamma. Okay, I'm going to define, so a cocycle is something which is defined so from the system to a group. Okay, so you have the system on one side and you have the group. Okay, so it's a cocycle. So it's a map that goes from gamma times X to K, which is measurable so with respect to the sigma algebra, and also satisfies this thing which is known as the cocycle identity. Okay. So okay, you can look at the identity, but this is where the definition comes from. And if you look at the action as a groupoid, for example, then this is just, and then the group is also a groupoid, so this is just the definition of a groupoid homomorphism. Okay, so you can think of a cocycle as some sort of a homomorphism from the action to a compact group. Okay, and the formal definition has to satisfy what is written here. All right, and then you can produce out of this data. So you have a measure preserving action and the cocycle into a compact group. And you can produce a different action of your group gamma in the following way. So you take your new space with which the group acts, it's just the product of X with K. Okay, it's just the Cartesian product with the product measure. So on K you put the hard measure. Okay, and you put the product measure on this. And then you define the action in the following way. So I have gamma and then I have okay, and then I have X and K, right? So this is an element in my product. So how do I act? So on the first coordinate, I use the old action that I already have. And on the second coordinate, I twist by the cocycle. Okay, just means that the action on the second coordinate, it not only depends on gamma, but it also depends on the X, right? Because there is this cocycle. And if you want this cocycle identity here, it is exactly the identity that makes this thing a group action. Okay? If you write what it means for this to actually be a group action, then this will give you this identity. Okay? So this is a classical way to extend, this is called a compact extension of an action. I mean, sort of a trivial way to do this, if you start with the homomorphism, if your cocycle does not depend on x, but only depends on gamma, then this tells you that this has to be a homomorphism from gamma into k. Oh, and then you just get this product action. Okay? But this is sort of, you can also do a non-trivial thing by twisting with the cocycle. Alright, so this is the definition. I have a compact extension. And now, what is a distal action? Okay, so there is one more remark here. So a compact action, I mean the thing that we looked at before, you can view this as a compact extension of the trivial action. Right? Because for the trivial action, then there is no x. Basically, there is only one point. And then you just get a compact action. Alright, so now here is the definition. So a distal action, so this has nothing to do with distality in NLP, but it is much older, so I think it definitely has priority. So a distal action is obtained by a transfinite series of compact extensions starting from the trivial action. Okay? So what do? You start with the trivial action. Okay, this is easy. Then you do a compact extension. Then you do a compact extension of this. Then you continue. And then at limit stages, well, you just take unions and then you go on.
But this is a theorem, not a definition, isn't it?
This is a definition. This is how you get the distal action. So everything that you produce in this manner is called a distal action. The fact that they exist, I mean, this is a theorem. This is a definition.
Yes. It was first of Bernoulli's theorem.
Well,
it's defined in different ways.
There is an equivalent definition which is Furstenberg's theorem. What I wrote here is a definition. I mean, you can take it as a definition. But, okay, should say that they're different things. So maybe I should say, I mean, if you have seen those things before. So there's a notion of distality in topological dynamics, where there is actually an intrinsic definition that does not involve this. And then there is something called Furstenberg's theorem, which gives you this transfinite thing from this intrinsic definition. Then, okay, but this is in topological setting. So in the measurable setting, there is a similar thing, except that the intrinsic definition is horrible. And it is due to Zimmer. It comes after. But somehow the other definition is very nice, and it's just this one. Okay, so again, so this was, this was introduced by Furstenberg in his proof on Severedi's theorem. And so it sort of plays an essential role in the proof of, the ergodic theoretic proof of Severedi's theorem, those distal actions. Okay, and so I should say that those things exist. I mean, it's not completely obvious that you can get non-trivial things in this way. So it's a theorem of Berenstein and Forman that at least when gamma is equal to the integers, for any ordinal, you can get an action like this, which has distal rank at least that ordinal. I mean, countable ordinal. So what is distal rank is just the minimal length of this, of the number of extensions that you have to do, right? Because maybe you can get the same action with different towers, but there's actually a canonical tower. I mean, sort of, if you just have a distal action, there is a canonical tower below it that is of this type, and the length of this tower is called the distal rank. Okay. So you can get, any ordinal up to on. Okay. All right. So here's an example of a distal action. This particular example is due to Parry and Walters. Just to sort of see what sort of things you can get, and those will be important in a second. So you start with the circle, and then with two irrational numbers, and then some map. Don't think about those too much. The numbers are probably important, but this is okay. And then I'm going to define a measure preserving transformation from this space, so t times t to the n to t times t to the n. Okay, so t is the circle, and this is just an infinite product of the circle. Okay, so this is going to be, I'm going to start with a compact action. So I'm just going to start with the irrational rotation on the first coordinate, and then I'm going to do a compact extension using the second coordinate. Right? So this is we're exactly in the situation that I was before. Okay, so I'm going to look at the definitions. I'm going to define now a measure preserving transformation from the object itself. So what does it do? Well, so on the first coordinate, as I promised, just doing irrational rotation. So you just translate by alpha. This is what you do on the first coordinate. And then on the second coordinate, the second coordinate is just all the rest. So what do I do on the second coordinate? Well, I twist. Right? So I take this W1, but then I also do something that depends on Z. Okay? Just, forget theta for a second. Just forget that, and then, okay, I just add Z. And then, okay, maybe I also add some other number back in the other coordinates. Alright, so this is a typical thing, the type that I just explained. So this is a distal transformation of rank 2, because you start with a compact action, and then you do one time, you do an extension, so you get rank 2. Those things, okay, this is the whole point of this alpha, beta, and theta, they can be chosen in such a way that you actually get an ergodic transformation. Okay, because it's not obvious, whether the transformation you get is ergodic, but you can choose those parameters here in a way that this is actually an ergodic transformation. Okay, and then let me define one more thing. Okay, so this doesn't work. Okay, now I'm going to define another map. This is a sigma, so this is going to be an endomorphism of my system. Okay, so it is going to be a factor map, which is not an isomorphism. Yeah, so this system is not coalescent. This is the whole point of the example. But this is a system where we have an endomorphism, so a self map, which is not an isomorphism. Okay, so what does this self-map do? Well, so on the first coordinate, on the z coordinate, I just add beta. And beta was this other number, yeah? Was this other number. Then what I do is, you see, I mean, it's basically the same sequence, except that I skip the first coordinate. And if you write it down, because here I add beta to beta and so on, I mean, if I do this and I add beta to z and skip the first coordinate, it's like a unilateral shift on the second coordinate. And so what happens is that, well, this thing actually, I mean, this is a factor map. So this commutes with S. So it defines a self-embedding of the system into itself, which is obviously not an automorphism because I just forgot one of the coordinates. So this map here is clearly not injective, so if you want the embedding that I get, the dual embedding is not surjective. Okay? So it's a nice example. It's due to Parry and Walter from the 80s. Alright, so this is the upshot of this is that there exist ergodic distal systems that are not holistic. Okay, so this thing that was true for compact systems is actually not true in general for distal systems. Okay. Alright, so there's this another theorem, it's in the same paper if you want to drop, so it's the same as the previous theorem, except that now the assumption is weaker, so we don't assume that X is compact, we only assume it is distal. But then the same conclusion holds, that if you have a distal action, and then Y is a strongly ergodic, okay, now we'll see how it goes. Okay. Y is strongly ergodic and then X is weakly contained in Y, then X it is a factor. Alright, however, we had this corollary from before, that I mean, this automatically implies that weak equivalence implies isomorphism. Well, this is, this doesn't work because of this example. Right? Well, but then you could still ask, I mean, okay, maybe it doesn't work, but this example is of course not strongly ergodic, right? Remember, we have this strong ergodicity assumption here. But this example is not strongly ergodic because it's an action of the integers. And then you could say, I mean, maybe they should have asked the question whether it's actually possible, with the additional assumption of strongly ergodic, I mean, to have an example like that. Because I mean, it's a natural thing to ask. For some reason, they didn't ask the question, which is very unfortunate because we answered it. But then, I mean, I talked to Robin afterwards, to Robin at the Cardrob, and then he said that, I mean, they didn't even think that this would be true, and they didn't ask, they didn't think too much about it. Okay, so here is the, well, this is basically corollary of our main results, is that if you actually, I mean, you do get this thing, that if the action is in addition strongly ergodic, so if you have a strongly ergodic and distal system, it is actually coalescent. So the thing that I just explained to you in the previous example, it cannot happen for a strongly ergodic action. So this is, okay, so in particular, I mean, if you apply the previous theorem, then you get that if you have two strongly ergodic and distal systems that are weakly equivalent, they have to be isomorphic.
That comes from, that theorem is based, comes from what you did?
Yes, this new theorem comes from what I did, which I'm going to explain now. In the, okay, so there's, I mean, there's no model theory in this theorem, right? I mean, this is just a completely ergodic theoretic statement, and there are no model theoretic notions. In the, okay, but now maybe I'll do a little bit about a little bit of model theory. 5 minutes. But I mean, the proof of this theorem is entirely model theoretic. All right. Okay, so let me just a quick reminder. So this is supposed to be an easy slide. It's about algebraic closure. So if you have A a subset of M, so a subset B so is definable if this distance thing is definable. So the distance to your set is a definable predicate. I mean, again, there's some subtleties in how you define what is the notion of definable sets in continuous logic, but this is the correct notion. Okay, so that you need the distance to be a definable predicate. So you say an element is algebraic if it belongs to a compact definable set. The algebraic closure is the collection of all algebraic elements, and the existential algebraic closure, well, is the same thing except that you require that the formula that defines your compact set be an existential formula. Okay, sorry, this is a quick slide, but I suppose those are notions which are familiar. Okay, so here is the actual theorem that implies the things from before. Okay, this also implies, by the way, the theorem by Yuan and Tokadrov. From this, you can very easily deduce their whole theorem, the one that I mentioned before. Okay, so it says that if X is a strongly ergodic system and Y is a distal factor, so if you have a subsystem which happens to be distal, well, then actually Y is contained in the existential algebraic closure of the empty set. So this is sort of a reminiscent of what Anand was saying, that it is because it is sort of a compact thing. It is actually, I mean, it is in the algebraic closure. But it's true not only for compact, but it's already true for distal. But the strong ergodicity assumption is essential. And this is completely false if you don't assume strong ergodicity. Okay? So I mean, there is something to do. Alright, so we have, I should say, we have two different proofs of this fact. So one of them just goes by induction. You just do induction on the distal rank, and then for the induction step, what you have to do is that if you have a compact extension, then you have to show that it is contained in the algebraic closure of the thing below. But again, so this uses the strong, so you have to find how to use the strong ergodicity assumption to do that. And then once you do the algebraic closure, you pass to the existential algebraic closure by a diagram. Yeah, so this then you can do things like that. And then the second one actually uses the Furstenberg-Zimmer theory about distal actions. So it uses different definition of distality, and then it uses some stability. So you have to ask Tomás about this.
But this is not a stable theory.
This is not a stable theory, but there's partial stability. I mean, there are some formulas. It uses your book. Okay, so Tomás, it uses something from your book that he claims works in continuous logic. You can talk to him after.
Thank you very much.
Well, I mean,
it
is quantified free statement.
Right.
Oh, quantified statements.
So quantified free statements are stable. I mean, all right. So let me say how you, quickly how you prove the corollary from the theorem. I mean, how you prove this fact from the algebraic closure. I mean, now if you start with any endomorphism, any embedding of X into itself, well, then remember, I mean, if X is distal, it is contained in the algebraic closure of the empty set. So it's just the union of compact sets that are defined by existential formulas, but existential formulas are preserved by embeddings. So you actually get this bunch of compact sets which are preserved, and then this is a standard fact that if you have an isometric embedding of a compact set into itself, it has to be subjective. Yeah? This is the same thing as for finite sets. Okay, and this is how you get this. So sigma has to be subjective just because of this, those compact pieces, right, which are embedded in themselves. Okay, so this is this. All right, but now there is this. This is a bit of an embarrassing question. I mean, so after we proved this theorem, we were very happy. And then when we talked to people, and I wanted some examples where we apply our theorem. And, okay, then we talked, and it turns out that actually actions like this, which are strongly ergodic, distal, and not compact. Okay, so compact things do exist, but once you go like one is, I mean, rank 2, if you want, is not known whether such actions exist. Okay, so now we're sort of seriously working on trying to construct one, and then the week after, we change our mind and we decide that they don't exist, and then we try to prove they don't exist, and we're not even synchronized. So I mean, I'm doing one, he's doing the other, and the next week it works. But we'll hope to be able to solve this. Okay, so this is a bit of an issue. All right, and then there is this last slide. So we have actually, okay, there's a second result. All right, so it's the definition. So a group gamma has Kasdan's property T if every ergodic action is automatically strongly ergodic. Okay, or equivalently, if you're a model theorist, you can define property T just by saying that ergodicity is an elementary property. Well, it's equivalent. Of course, you can imagine Kasdan did not define property T in this way. And so the equivalence of this definition with the original one, which you may have heard about limited representations, is due to, I mean, there are two directions in the equivalence, and actually, so one of them is due to Cohen-Weiss, and the other one is due to Schmidt. I mean, Schmidt was the guy who introduced strong ergodicity in the 70s. And so this is one of the things he proved. And then Cohen-Weiss proved the other direction. Okay, so examples of property T groups, I mean, if you haven't seen them, so it is, so things like this. So this is the example people always give, so SL3Z. Or more generally, so lattices in high-rank real Lie groups. Like this one is a lattice in SL3R, and then similar things. I mean, if you have other Lie groups, you can take lattices; they have property T. And also things like random groups. I mean, there is some way. I mean, so Gromov has sort of probability law on groups. I mean, on generators and relations, and then almost surely you get a property T group. And there are also many other property T groups. I mean, it's a big class, big and important class of groups. And then for those, we actually prove that we can prove that those things, I mean, distal, non-compact, strong. I mean, strong ergodicity is automatic. So just distal, non-compact, and those things actually do not exist. Okay, so you cannot make a non-trivial extension. Okay, so here is the theorem. So if gamma has property T, then if you have any distal action, it's actually compact. So it collapses. I mean, this whole hierarchy that for Z goes up to omega 1, for property T group, it collapses to the first level. Okay, so there is, I mean, this uses, okay, so this theorem actually uses the theorem from before about the algebraic closure. And also, okay, so this result was also obtained by Kifan and Peterson, but I mean, they use operator algebra. Okay, so it's a different, it's entirely different. Okay. But they, I mean, I think that they never publish it, so there is no, yeah, I think I'll stop here. Thank you.